Hello everybody and welcome to our first lesson in physics. Today we're going to be reviewing some things that hopefully you have heard of before and have worked with in prior physics classes. So we're going to be reviewing motion and kinematics. Before we really get into that, we need to establish the difference between a scalar and a vector, because in physics it's important you understand what you're dealing with. Because it frames your thoughts for a lot of different problems. So a scalar quantity has only magnitude, meaning it only has like a size, right? You can think of magnitude as a size. Whereas a vector has magnitude and direction. Usually this direction is going to be indicated via either like a vector or a sign, like a plus or a minus, like a sign, like it might be positive or it might be negative. So some examples of this are scalar quantities are length, area, volume, speed. Let's also add over here, it's not on this one, it's also distance, right? Distance is a scalar quantity. It's just how far you go. And then vectors are magnitude with direction. So if you think about speed, you might be going 50 kilometers per hour on the road. That's just telling you how fast you're going. It's not telling you what direction you're going, right? Whereas velocity might say, oh, you're going negative 55 kilometers per hour, which basically what that means is you're going towards the negative direction, which if you were on like the x-axis, your negative directions would be to the left. So it's telling you that, you're going to the left at 55 kilometers per hour, right? So that has a direction and it tells you the magnitude, right? And so we're going to be, in this course, we'll be talking about all of these things here, as well as over here we'll be talking about mass, speed, work, power, energy, and so all those things you're going to need to understand when you're working with a scalar and when you're working with a vector. So we're talking about motion. So the first thing we'll discuss with motion is distance versus displacement. Remember, distance is a scalar, displacement is a vector. Right? So distance is a terrible definition of distance. Distance is the total distance, total path traveled. It's easy with an example. Total number of steps traveled, total number of miles traveled, total number, whatever you traveled. Whereas displacement is the change in position. This little graphic kind of gives you a nice setting for that. Let's pretend you start here. Whatever you walk on this path over here, right? And you walk and you walk and you walk. And maybe you walk, like maybe this is 2.5 kilometers, right? You had a nice hike through the woods, and you walked, like if you looked at your phone, the step counter is going to tell you, hey, you walked 2.5 kilometers. That is your distance. However, you end up here, which let's say this is only 1 kilometer away from where you started, right? If you had just walked in a straight line distance, you'd only be 1 kilometer away from where you started. That's your displacement, right? It's a change in your position, how far you are from where you started, right? So another good way you might think about this is how far from the start. All right, so let's look at an example. These examples usually help us frame our thoughts here. If you take, so you're starting here, you take 3 steps forwards and 2 steps backwards, right? So 1, 2, 3 steps forwards, and then you decide to go 2 steps backwards. The question is, what is your displacement? What is your distance, right? So distance, remember, is total steps, the total distance traveled. So the number of steps I took was 1, 2, 3 forward and then 2 backwards. That's a total of 5 steps, right? So the distance traveled is 5, whereas the displacement, in this case, is how far am I from where I started? And you are here at the end, right? So you are only 1 step from where you started. So the displacement in this case is 1 step. And the way you could calculate displacement is, remember, it's change in position. We're going to use this delta symbol for change. So it's change in position. If you think about when you started, so the change in position can be the final position minus the initial position, right? So my final position was 1, my initial position was 0, right? If we thought about this as a number line, right? This was 0 steps, 1 step, 2 step, 3 steps away. And so if I do final position minus initial position, I just get 1. And let's look at another one. I take 5 steps forwards. So again, let's just say we start here. Think about it as a number line. I start here at 0. I'm going to take 1, 2, 3, 4, 5 steps forward. Then we're going to take 7 steps backwards. 1, 2, 3, 4, 5, 6, 7. We would ask, what's the distance? Well, the distance is how many total steps did I take? Well, that's 5 plus 7, right? 5 forward, 7 backwards, 12. The total distance travel is 12. This is what my step counter on my phone would say. Whereas if I just want to know the displacement, then I'm thinking change in position. Change in position. And as you can see, what you may notice is I went backwards some, right? I ended up -2. Like if I had this on a number line, I would be at -2 on this number line because I walked 7 backwards. So I'm like to the left. This negative symbol symbolizes that I am to the left of where I started by 2 steps, right? So I'm left by 2 steps. And again, we could calculate this. We could have gotten this one by the final position minus the initial position. In this case, the final position was sorry, that we're thinking about the d initial, d final minus d initial. The initial was, oh yeah, I'm thinking about this wrong. df is going to be 5. Hold on one second. Let me think about this. Yeah, okay. So we're just thinking about my final position was -2. My initial position was 0. And so my displacement is -2, which is the same thing right over there, right? So that's something important to note just between distance and displacement. And then the next thing we want to talk about is, okay, so that's just telling us where we are and how far we've gone. Another important part of quantifying motion is talking about speed, which is speed is a rate, right? So it tells us the rate at which an object covers a distance, right? You may be familiar with the equation distance equals rate times time. This is true. The d is for displacement if the r is in speed. And you could solve this one for your rate, and you would get the rate is the distance over the time. And that's what this is saying here, is just speed is distance over time, right? So as an example, you did this on the pretest. If Usain Bolt, the fastest guy in the world, ran 100 meters in 9.58 seconds. If I want to know his speed, then I'm just going to say, okay, well, speed is going to equal the distance he ran, which is 100 meters in 9.58 seconds, right? And if you divide those two, then you will have his speed. Okay, so I went ahead and got my calculator out and did 100 over 9.58, and I got 10.44 meters per second, right? So he can run about 10 meters, 10.4 meters every second. What's important for you to understand is that this is an average speed, right? He did not run 10.44 every second. He probably was a little bit slower, and then he sped up, and then, once he got going fast, then he was running at a constant speed. But in the beginning, he had to, he was stopped, so he had to kind of speed up. So that's, again, speed, distance over time. When we get to velocity, which remember is a vector, we have to use displacement over time, right? Remember, displacement was a vector quantity as well. And so usually the way we're going to do this is velocity is displacement over time. You want to think about this as change in position. Remember that triangle thing represents change, that delta is change. Change in position over change in time. And one way to find this is to do d final, and d represents position, over d initial. So wherever you ended minus wherever you started, over your final time, however, what was the time when you ended minus what was the time when you started. And so that, and this usually gets abbreviated as df minus di over tf minus ti. You may recognize this as the same equation when you're doing math. It's just slope, right? That's all this is finding the slope of something. So as an example, you might be looking at You might be looking at an graph like this, and you might be asked to find, hey, what's the velocity of the runner? Let's find the velocity from t equals 0 to t equals, let's do 600. Right, so we look at this, and let's just say this is at 600. It's a little bit off, but just for the sake of this problem. And then, you know, this point here is 600, and then 700. Right, and so if we wanted to find the average velocity, again, it is average. Instantaneous is something else. You would simply take the final minus, sorry, not the final, the displacement final minus the displacement initial over the time final minus the time initial. In this case, the final displacement is 700, right? Because he's ran 700 meters after 600 seconds, so it'd be 700. The initial displacement, well, he started at 0, so it would be 0 over the initial, the final time was 600. It took him 600 seconds to get there, and the initial time was 0 because he started at 0, 0, right? We're basically just finding the slope, the rise or run of this line, and if you do this, you get 700 or 600 or 7, 6. Make sure you put the units, right? This was measured in meters, and this one was measured in seconds. So it's 7.6 meters per second, or 1 point something meters per second. Let's look at another example. Let's say we want to find the displacement, or sorry, the average velocity from t equals, let's do here, that is 900, from t equals 900 to t equals, let's do, what's a nice one here? Let's do this one there. That's 1,200. So to t equals 1,200. Right? So what we need is right, average velocity is going to be change in position over change in time, which again is just the df, the final minus the initial over the final time, t final minus t initial. So in this case, this point here is 1,200, and the y value is right about there, which is 25, 26, 27, 28. Right, so this is the final time, and this is the final distance, or the final displacement. And so if we're doing our velocity, we would get 2,800 minus our initial position. In this case, we were at 900, and then that value there was 1,000. So this is the final displacement, the final position. So we'd have 1,000 minus 1,000, and then we'd subtract the times, right? The final time was 1,200 seconds, the initial time was 900 seconds, and you'd end up with, 1,800 over 300, which, of course, simplifies to 6 meters per second, right? These are measured in meters, these are measured in seconds. So the average velocity here, from here to here, between there, is 6, and maybe you recognize that's just the slope of this line is 6, right? So that's a brief introduction to how you would find average velocities. Okay, so as you know, not all objects travel at a constant velocity, right? Their velocity may change, they may speed up, they may slow down. Just like an example with Usain Bolt, like he starts at 0 and then he speeds up and gets to a certain velocity. He's not running at the same velocity the entire time. So a change in velocity is called acceleration. You can find it by doing change in velocity over time. I always like to think about this as change in time, right? So because that does affect you sometimes. So this acceleration basically is change in velocity over change in time, which you can find change in velocity by finding the final velocity minus the initial velocity. And you can find the change in time by doing the time final minus the time initial. So let's look at an example here real quick. Okay, so a very simple example might be a cheetah goes from rest meaning stopped, to 25 meters per second in 2.5 seconds. What is its acceleration? So remember, if we're talking about acceleration, and again, this is average acceleration. When you talk about instantaneous, that's going to be like the next level of physics if you choose to do that. Change in velocity over change in time. If you want to think about this situation up here, think about what is the initial velocity? Well, it's at rest. The initial velocity is 0 meters per second. And when does that occur, right? So what's the time, the initial time? Well, that's also 0. And then the final velocity would be 25 meters per second. And the time would be 2.5 seconds, right? So if we're doing that formula up there, you know, the final velocity minus the initial velocity, we're going to be doing 25 minus 0, right? We're subtracting these, over 2.5 minus 0, and we get 25 over 2.5, which is going to be 10. 10, right? You get 10, and then remember units, right? These were measured in meters per second. These were measured in seconds. So you have meters per second, right? Because think about your units, right? Your units were these on the top, 25 meters per second minus 0 meters per second. So this is in meters per second, and your bottom was in seconds. So you have meters per second, which is the same thing as 10 meters per second squared. And so that's also an important thing for you to understand, is that acceleration is always measured in meters per second squared, or maybe not meters, it might be kilometers, whatever, but the time unit is always squared, because you're trying to figure out how much did the velocity change every second, right? A rate per time. Okay, for the last part of this lesson, we're going to do a little bit of an experiment. And you know, if we were in class, we'd be doing a lot of dropping things and measuring things. But I'm just going to try to demonstrate this for you as we go. As we drop this, I want you to think about what's the displacement and distance, find the velocity and speed, and then find the acceleration, right? So here we go. We're going to start. We're doing a shuttlecock. We're dropping it from 3 meters, and we're dropping it in air. Let's go ahead and do it, and you can see that the time it took for it to go from 3 meters to the ground is 0.9 seconds, right? So we're going to log some data here, right? We're going to say, okay, well, time, and let's start with height, right? Height is a function of time. If you want to get into physics and math, they're basically the same thing. Just physics is like applied math, right? So at time 0, the height was 3, right? Before we started, the time was 3. And then after 0.9 seconds, the height was then 0, right? So if I want to talk about displacement, remember we said displacement was change in position, which is basically in this case, we're talking about height, so it'd be the final height minus the initial height. Well, in this case, the final height was 0, right? Hence 0. And the initial height was 3. And so the displacement is -3 meters, right? Which is basically saying that, you know, that shuttlecock went down, right? The negative is saying down by 3 meters, right? If I was talking about distance, then I would just be asking how far did the shuttlecock travel, right? And the answer to that is 3 meters. It traveled 3 meters from up here to down there. Displacement is a scalar, so we don't care about what direction it traveled, just the fact that it traveled 3 meters, right? If we're talking about velocity and speed, remember velocity is displacement over time. We already calculated our displacement is -3 meters, right? So -3 meters over time. It took 0.9 seconds, and so the velocity is going to be -3 divided by 0.9, which is -3.33. Don't forget units. meters per second, right? Because this was measured in seconds. So the velocity, the average velocity is negative 3.33 seconds in that time, from time 0 to 0.9 over the entire trip of the thing, of the shuttlecock, right? If I wanted speed, remember speed is just distance over time. The distance was 3 over 0.9, and so the speed is 3.33 meters per second. Now you might just say, oh, well, the speed is always just, the absolute value of the velocity. And in most things we do in this course, you are correct. But when you get to more advanced physics, that will not be correct anymore. So just try to keep that distinction for yourself. Then we might ask about acceleration. Well, acceleration is change in velocity over change in time. So you might think, okay, well, what was so the final velocity minus the initial velocity over the final time minus the initial time. You might say, well, what was the final velocity? The final velocity right before it hit the ground was negative 3.33, right? So you don't want to think about it once it hits the ground, because then it stopped. But right the moment before it hits the ground, it was negative 3.33. What was the initial velocity? Well, that was just 0, right? When we first dropped it, we didn't throw it down, we just kind of let it go. And then the final time was 0.9, and the initial time was 0. Keep in mind, this is meters per second, and this is seconds. So we're going to do our negative 3.33 divided by 0.9, and we're going to get negative 3.7 meters per second squared. And this is our average velocity over the time frame when the shuttlecock was dropping. Let me show you what I mean by shuttlecock, like average. If you actually look at the values for this, you can see that the velocity is changing, right? The velocity is increasing over the whole interval. If you found the average of all these numbers, right, add them all up and divide by how many numbers there are, you would get about negative 3.3. You can also see the acceleration is changing, right? It starts off with a very high acceleration, and then the acceleration gets lower. If you found the average of all these, you would end up with about negative 3.7. Ooh, that doesn't look right. Okay, that's a little bit different in this case because of the shuttlecock thing. But this is actually the, oh, I know what this is. This is the final acceleration, because you're finding the acceleration at the end here. But the idea is the same. So if you had more precise measurements, you could get more precise measures of these things. All right, so that's it for the lecture. I'm going to post some problems. I'd like you to try the problems, and then reach out when you have questions. I can make a quick video, or I can just answer your question via text. But it's really important that you ask the questions, especially early on in the year. You don't want to fall behind on stuff. That'll just make the rest of the year really hard.